Hi friends, welcome back. This is day 10 of doing Codeforces until I become specialist, and today we are going to solve remaining problems of 818 in TLE eliminator city sheet. Okay, good. Uh, this is 26th problem. Serval and Mocha's array. So Mocha's likes arrays and Serval gives her an array consisting of positive integers as a gift, and Mochas thinks that for an array of positive integers A, it is good if and only if the greatest common divisor of all the elements in A is no more than its length. And for an array of at least two positive integers, it is beautiful if all of its prefixes whose length is no less than 2 are good. For example, okay, now what we have to do? Uh, Mocha gives you a gift array of n positive integers. She wants to know whether array A could become beautiful by reordering the elements. So it's allowed to keep the array A unchanged. So unchanged means we are not able to add or delete existing element in the array. So input. So we have to read number of test cases. For each test case, we have to read length of this array, and then we have to like read n number of array elements. After that, we have to print as an output if it is possible to reorder the elements in A to make it beautiful. Okay, otherwise we have to print no. But before that, as I already submitted these codes, so I don't type them again, but I will explain the intuition behind them. So for this, let me copy all this. Okay, uh, let's try to understand this. Okay. So what we have here, this is the number of test cases. There are total 6 test cases, and for each test cases, we have to read n value, which is nothing but the length of the string. So I'm reading 2 is my length of the string, and and then after I have to read two elements, right? So one is 3 and 6. So now we have two elements. We need to reorder them in such a way. Is it possible? And we have to find if it is possible to get uh, to make the array as beautiful or not. And array is only beautiful when it is only beautiful if GCD of all prefixes is less than or equal to length. So of all prefixes. So this is what he's mentioned in the question. So if GCD of all prefixes is less than or equal to its length, then it's a beautiful array. So we have to check. For that, we can reorder. 3. If we change its order, we can get as a 6 3, but its GCD is 3, but which is not actually less than or equal to its size. The size is 2, right? So that's why here we have to print no. So now as an output. Under 1 2 4, here 1 2 4, if the prefixes of 1 to 4 are like 1 2 and 1 2 4, here 1 is also a prefix, but we have to take the prefix which have length which less than which is like we have to take the prefix which has to be a length greater than or equal to size 2. So that's why we are not taking 1 as the prefix. And for this prefix 1 2, which whose GCD is actually 1. So if GCD is less than or equal to its length, the length is 2. So 1 is length in less 1 is actually less than 2. So it is right. And 1 2 3, the GCD is actually 2, right? So which is less than or equal to size 3. So true. So that's why uh, it is a beautiful array. We have to print S for that. And for 361, right? We know that 361, if we are not changing its uh, if we are not changing changing, like if we are not reordering the elements, definitely 361 is not a beautiful array. So we have to reorder that. After reordering, the array becomes 1, 3, and 6. Now this is one prefix and this is another prefix. We have two prefixes, and so the GCD of this prefix is actually 1, which is less than or equal to 2, and GCD of this prefix is actually 3, 3, yes, 3, which is less than or equal to size. What is its size? 3. So okay, now it is also true. So that's why we have to print here true. For this test case also we have to print S. I think you understand the intuition behind it. So every time what we are actually performing, we have to find the GCD between two existing elements, and if the GCD is actually less than or equal to 2, then we have to print S. Otherwise we don't we have to print no. Like if you take an array as 2, 4, the GCD is obviously 2, and if imagine an element is added like 8, even though the GCD won't change, but if it is 7, then the GCD of it is changes to 1, which is less than or equal to 2. So changed GCD is also less than or equal to 2. But here 136 in this, the GCD is actually 3, even though which is not less than or equal to 2, but here it is actually less than or equal to its size, so that's why it's accepted. Okay, so let's see the code. Okay, so what we are actually performing, we have to read the test cases, and then after we have to read the size of the array. So up to here I think we are actually reading the array, and after that we have to find the GCD of the element of the adjacent elements in array, not exactly adjacent element, prefixes of the array, and prefixes whose length has to be greater than or equal to 2. So that's why here the first loop is start from 0, and second loop is starts from 0 plus 1, which is actually 0, which includes both 0 and 1 indices. So the length now becomes 2, so it's satisfied. So that's why we have to increment uh, we have to write jth iterator as initialize jth iterator as I plus 1. Okay, and then after now we have to check whether the GCD, yes, I forgot, this is the function which gives the GCD of two numbers, which is present inside the STL of C++. Okay, and now I have to find the GCD of two numbers. If it is actually less than or equal to 2, then it is true, and then otherwise we have to iterate, we have to find if there is exist at least one GCD which is less than or equal to size 2, then the GCD is true. So if the GCD is true, then we have to print as, otherwise we have to print no. I hope you understand. If you don't, just read the question again, then you will. Okay, the GCD has to be same. Okay, so the question actually bit easy. Without reordering, we won't get a beautiful array. So it lies in it. 1 and 2, which is 27th, I think. Yeah, 27th. We have a sequence of elements. Okay, an array which contains only two elements, 1 and 2. Okay, it's a kind of interesting one. I already solved it. Let me explain. So just read these statements. It's very important. In order to become an array, so like in order to print, how can I say? So we have an array, and then I think this. How can shit, it's so this question is actually okay. So what we have here, there is an array which contains elements from a1 to an, and find out the integer k exists such that we have to find out the integer k, so which is actually between 1 less than or equal to the size of the array n minus 1, right? And then uh, these are all the elements of an array. So actually a1 is actually presented at 0 index, right? So we have to find an element ak such that the product of the elements from a1 to ak is actually equal to the product of the elements from ak plus 1 to the an, right? If if we are able to find that k value inside the array, then we have to return the position of the k, the smallest position of the k, right? Otherwise we have to return like otherwise we have to return minus 1. Yes, so these are all the test cases. So let me copy and open this. Insert. Okay. Okay, right. Back to back. So we have to delete them and now. Okay, cool. So this is 27th problem test cases, and how can we actually obtain the intuition behind it based on the test cases? And it's so easy. The question itself says that uh, the array only contains two elements. One is 2 and another one is 1. So it contains like this. 1, 2. So we can thought like we can think like uh, we have to find how many twos are there, and then half of where the half of the twos are actually exist, then that's the position we have to return. Otherwise we have to return minus 1, and that intuition is absolutely right, because here is the deal. No matter what, how many times you multiply, how many times you multiply 1, you can get 1. But when you multiply with other than 1, the result is actually affected. So when you multiply two twos, we can get the result as 4. When three threes, we can three twos, we can get the result as 8, like that. So here also, and what we have to do, we have to return a position such that the elements like take the 0, 0, 1, 2, 3, 4, and this is like let me draw Okay, so we have let us take an array. So an array which contains elements as 2, 1, 2, 1, 2, 1, and 2. Now position 0, 1, 2, 3, 4, and this is 5 and this is 6. Okay. Now 1, 2, 3, 4. There are total two forces are there and 4 by 2. So and 4 is an actually even number. So we can get half of 4. So 2 where the second 2 is present, that is our index. We have to return. So second 2 is present here. So we have to return this index. So 2 plus 1 is the our answer. Why 2 plus 1? Because it's a zero based index, right? So if we consider this 2, 2, 2, 2. So here also 4 2s are there, where second 2 is present here. And its index is actually 1, and we have to return 1 plus 1. The answer is 2. See, and here we are not able to find a position k such that the products of element from 0 to k is not equal to the product of elements from k plus 1 to n, right? So if we take the if we take this zeroth position is actually k, then 1 is the answer here, but here 2 is the product, so which is not equal. If you take this one, then 2 is actually present here and 1 is present here, which is again not equal. So that's why we have to return -1. And like this is the name approach, this is what the question says about. And here 1 1 1, so 4 ones are there, and like this is kind of edge case. 1 1 1 1, so all are ones. And if we get even number, it's not about even or odd when we are dealing with ones. I already told you, right? So one won't have any effect on its result, no matter what, how many times one is multiplied itself, the result is actually one. So for these, the k is actually at zero position, right? So when 0 to k, I say k is actually 0. So the answer here is actually 1. And here, the product of all these is also equal to 1. So equal. So we have to return this zero position as we have to return based on one based indexes. So we have to return 1 is the position. So that's why here 1. Okay, so hope you understand this question. So let's see the approach. Let's see the code. Just what we are seeing it now. Okay, what we just know now, that is the code. See here. See here. Come on. Okay, so we have an array, and what I'm saying, we have to find number of twos, or how many number of twos are present, because one won't have any effect on the product's result. So how many twos? If the twos are actually odd, then we won't able to achieve the kth position. So that's why we have to return -1. But whenever the two are even, then we can achieve the k position. Not to achieve, we just have to find the where is the uh, um, where is the half of the 2 is present. Like if the result is 4, then and half of the number of twos are present, like, yeah, we have to say it like that. We have, if the total number of twos are 4, then we have to find half of the total number of twos, which is nothing but 2. So where the first two twos are present, that is our index. So for that, I'm taking an iterator. I'm taking a variable not to store the half of the twos. So if whenever the half of the twos that I'm calculating is equal to the uh, tot uh, total half of the total values of half of the twos, then we have to return its position. You know that why we are actually adding -1. So and then we have to break. So think you got it, this one also, and make it beautiful. So this is 28th one, array. So it's an ugly, it contains at least one element which is equal to which is sum of its preceding elements. Okay, and what we have to do is like we have to reorder. It's like a kind of the previous question. So we reorder type. So and here there is a hint. The elements are actually in sorted order, and the array is itself ugly whenever it is in a sorted order. So we just have to make the sorted order into unsorted order. Then the array automatically becomes beautiful from ugly, right? So this is what he's saying. Let's try to understand with the help of test cases, right? So, so let's paste the test cases here. Okay, then let's try to understand the test cases. But before that, we have to understand the problem, and the problem is about the array is actually in sorted order because we have this, right. This line actually says that the array is this line. So it says that this line actually says that array is sorted sorted order. That means we have an array elements as like 1 1 2 and 3 and 4 and 5. So the array is ugly whenever the element is the sum of the elements of the, like whenever shit. So the array is actually ugly whenever uh, the sum of the preceding elements for a particular element is actually it's the element itself. Like here for the element 3, the sum of its preceding elements are actually 3, which is the element 3 3. So then it is an ugly, it's an ugly, and we have to make it into a beautiful array. So that uh, for every element in that array, uh, there is not possible to get the sum of its preceding element as the same of that element, like this here. So for that, as it is sorted, we just have to make unsorted, and nothing but we have to place the largest value before at the 0th position. That's enough. We can, that's what we can do, right? To make it into an unsorted, like now after changing the array, it becomes 5 4 and 3 and 2 and 1. Now no matter what, we can't able to get the sum of the elements is actually equal to the element after it. Like check here. So 4 no, and for 3 5 plus 4 not possible, 2 not possible, 1 not possible. So I think you understand here. Check this. So 3 3 6 6. So here 6, 3 plus 3 is actually 6. So it's an ugly element. So to make it into a beautiful element, we just have to keep these 6 here. So then it becomes okay, yes, this is also one of the way, but we have 6 3 3 6. It is also an answer, right? Because it's not possible to get the element when we are adding the preceding element, some of the preceding elements as same of and as same as this element. Like hope you understand. So this is intuition behind that. Let's try to see the code and understand how you are able to write that code. Okay, so see here we are just yeah, I forgot to discuss about the first case, like edge case. There is an edge case here. Whenever we are sorted, whenever we are sorted, like yeah, this This is the edge case here. So 10, 10. So whenever we are sorted, the result is actually the same as before element. Like if the array is first position and the last position elements are same, then we can say that the array consisting only one element. Okay, whenever it consisting only one element, if you're not able to make it beautiful. Why? Because the elements are inside the array are actually same. No matter what, how many times you are reordering, you can get the same as before. Like so, for this type of condition, we have to print directly. No, it's not possible. So no, as an output. So see here for this, no as an output. Hope you understand this. Now, yeah. So after reading the array, I have to check the array that I am reading is actually sorted array, right? So if the first element and last element are equal, we have to print no. Otherwise, we just have to print the last element it first, in order to make that array into an unsorted array. So and then I'm printing the elements uh, from first to the last element minus 1. So now the array is unsorted. Basically, we are not actually made the unsorted array, right? We don't need, we have to print either yes or no. If it is yes, we have to print at least one possible way why you are actually printing yes. That's all it's about. Okay, hope you understand this one also. Now everybody likes good array. This good, bad, what is this? So everybody likes good array. An array A is good if for all pairs of adjacent all pairs of adjacent elements are different parity. Okay, okay, I got this one. So he's saying that it's all about choosing different parities. You know, what is the parity means? Parity means here it's an odd or even. Got it? So whenever array adjacent elements of an array are actually same parity, then the array is actually not good, like that. And whenever it is not, then the array is actually a good array, right? Uh, right. And then so we just have to make the good array. See here. In one operation, you can select any pair of adjacent elements in which both elements are of same parity and delete them and insert their product in the same position. We have to insert the position in the same position, and we have to minimum number of operations to form a good array. Like good array, a good array is an array which contains no two adjacent elements having same parity. Parity, it's like no same or even numbers. Uh, no numbers are odd or even. So it's about parity, not the value inside it, right? So let's try to understand with the help of example test cases, right? So here, but basically, let's understand what he's saying. For the array 1, 7, 11, 2, 13. So this is the array. Oh God. Okay, it looks like an array. It looks like an array. Okay. So 0, 1, 2, and 3, and this is 4. Cool. So what we are up to, we have to find whenever adjacent elements are same parity, we just have to delete there and insert their product instead of them. So here two adjacent elements which are having same parity. So what we have to do, we have to delete there. We have to delete them, and like here 1 and here 7. Okay, and insert their product. So 1 into 7 is actually 7 inside here. Okay. Now we have to iterate from here to here. So these two are also same parity. So what we have to do? We have to know their multiplication. 11 into 7, know their product value. 11 into 7 is equal to 77. And we have to delete their, delete them. Oh shit. Okay. Then we have to delete them. And instead of that, we have to insert the position, which is 77. Right? Now, we have to iterate from here to here. 11 and 77 into 2. So actually 77 is an odd parity, 2 is an even parity. So no problem. Now iterate. 2 is an even parity and 13 is an odd parity. So no problem. Now how many times we are actually performing product operation here? 2 times. So then 2 is our answer. See here, 2 is our answer. Okay, so this is just the way that the question is. We are just go with that flow. Okay, we don't actually use our knowledge here. We just actually do what we say. But it's just a basic question, kind of like all 800 problems are kind of basic questions, right? So we have to know uh, how to find how to accurately use the for loops and conditionals and understanding the question. That's what important for 800 kind of problems in CP, right? Uh, See here, so depending upon the question, 1, 7, like, let me take the second test case then. So 1, 2, 3, and 4. So for the first, we have to take this 2. So whose parity is actually 1. 1 means it's an odd. Odd means the parity is 1. And for even, the parity is 0. Just remember that even parity is 0 and odd parity is 1. Now we have treated from here to here, that means the rest of the array. So this is 2, which is even parity. As it is even parity, so compare the two parities, so odd and even, which are not same. So okay, no problem. Just increment the uh, iterator. Then so now the parity here, it becomes actually even, right? So 0. Now we have to compare that with the 0 parity. So odd parity is actually 1 and 0. No problem. So not same. Now 4. So it has parity as 2 and it has parity as 1. 1 is not. I mean, sorry, it's an even. Even parity means 0, right? So 1 is not same as 0. So no problem. So we now we are out of the array and the sum is actually 0. Number of operation. We just we print that. So 0 is our answer, right? And for this, so 1, 1, 2, 2, 2, 3. Now 1, 1, 3. So these 3 are actually odd parities. So for that, how many times you are performing the multiplication operation? It's simple. 3 minus 1, that is 2 times you are performing the operation. Why? Because 1, 1, 1. So 1 into 1 multiplication, the result is stored here. Now 1 into 1 multiplication result is stored here. So we are performing 2 times product operation here. So that's why 2 is the answer. And for 2 even parity, the sum is even parity whose parities are same. So we have to perform again the operation, but how many times? Only one time. So 2 plus 1 plus 0, so which is 3. Hope you understand this one. Let's see the code. Okay, so see here, after reading the elements inside the array, uh, we are we have to store how many operations we are performed along with the parity. And initially I thought I have an even parity. So for the first element, if it's an even parity or odd parity, if it is an even parity, then p is 0, and if it's an odd parity, then p is incremented to 1. So now we have to iterate over the rest of the array, and whenever I get the even parity, whenever I get the two parities are same, then we have to perform the operation. But here there is no need to perform the operation. We just have to print how many operations required. So increment the operation, operation variable, so O plus plus. And if there are not same parities, what we have to do, the previous parity is the parity of the current element. Right, see here, uh, here the parity is 1, and for 2 the parity is this first element parity, which is 1, and for 3 the parity is not 1. For 3 the parity is preceding elements parity, which is nothing but 1, right? So for the logic we are implementing this condition. So whenever then the current parity is actually equal to the parity plus 1 divided by 2. So we don't exactly use that condition. We can also write it as like parity whenever the parity is actually if 0, then we just change it to 1. Otherwise we just change it to 0. So like we can use conditional statement there also, no problem with that. And finally we have to print how many operations are required, right? Cool, hope you understand that one. And extremely round, so it's kind of a pre-computation problem. See here we have so here extremely round number is a number or a digit which contains only one non-zero number. So all this contains only one non-zero number, and if it contains more than one non-zero number, then it is not an extremely round value. And what we have, we have n as an input, and we have to print how many extremely round values are present inside the array. So uh, if you think you can easily get it, uh, like even a brute force approach, name approach is also good for this one, but we have to code a lot for that one, right? So the problem saying like we have a number n, and for that n we have to print how many extremely round values are there. Extremely round values are there, we can say that. So extremely round values are there, and extremely round value is a value which contains only one non-zero value, a non-zero digit. So value is nothing but here digit. Now, and the constraints. So here, this is the size of the array. We don't know, but the n value has to be okay. So it's here, right? The n value has to be less than. See, this is the n value. N value has to be less than or equal to 99,000, 99, 9,99,999. So basically we can say it as below integer range, because the integer range is 10 to the power of 9, right? So we can use integer for this. uh, so as I said, we have to know in these n numbers what are exactly extremely round number, and store them inside an array A. Now this A actually contains all the extremely round numbers of this n value. Now uh, take read the test cases from the user, and he said he gave a value n. So and now we just have to check whether this n is actually greater than or less than or equal to the element which is present inside the array. So until we are getting greater n is greater than that array current element, we have to add we have to actually store the values inside them. Sorry, we have to increment total number of extremely odd values. then we can easily return the total extremely values present inside the array. So this is what we have to do. I hope you understand. See, let's see the code for that. So see, I'm taking an array, and what I have to do, I have to iterate up to uh, the given size, and I have to store the element inside the array when that element is actually an extremely round. So for that I am using a function to check whether it's an extremely round or not. So the function is like first converting the given n value. Why we are actually converting the n into a string? Because the number n, it's really hard to say. It's not that much hard, because if we take uh, like a number 100, if we take a number 100, then when we divide it by 10, so this one cancel, this one cancel, and this one cancel. So one, only one non-negative integer. But when we take 11, and when we divide it by 10, 1 1, so we have more than one non-zero values, so we have to return false. Now to implement this code, what we exactly do, we have to write a while loop first, and while n is actually greater than 0. So for when greater than 0, what we are doing, we are getting their reminder. So n by divided by 10, so we have reminder. If reminder is actually greater than or like, yes, it has to be greater than 1. So whenever the reminder is actually greater than or equal to 1, we have to use a variable like say I, we have to increment I value, so which is actually storing the number of non-zero digits. And whenever this number of non-zero digits is actually greater than 1, we have to return false. Otherwise, after completion of while loop, we have to return true. Similar approach, but here I'm using a string because it makes code more clear. So I'm just turning that number into a string and taking each character. Whenever each character is not equal to 0, I have to increment this I. So if I is greater than 1, we have to return false. So hope you understand that one. Now from here, I have to read the test cases. For each test cases, there is an n, right? And for each n, we have to return how many total number of extremely round values present inside that n, up to n. So for that, I have to write a while loop and taking the element of array I. If that array element is actually less than n, I have to increment that index. So where that actually uh, array I is actually greater than n, that that is the point where I have to stop. Or if the I has to be less than the size of the array, right? Because if the size is crossed from out out of array, that means uh, it's not under the constraints, and simply we don't need to take them. So and then finally we have to print the I, which shows number of extremely round values. Okay, hope you understand this one, right? Let's go uh, the last problem, two permutations. So two permutations, you are given two integers and a b, and determine if there exist two permutations p and q of length n, for which the following conditions are hold. And the length of the longest common prefix of p and q is a, length of the longest common suffix of p and q is b, right? Right, okay. What we have to do, we have to find if there are two permutations p and q are exist, such that uh, the longest common prefix of the p and q is actually a, and longest common suffix of p and q is actually b. If it is not then we have to print no. If it is there, we are successfully finding the permutation, but we don't need to print the permutation. So then we have to print s. So like what's this thing? Uh, let's go to the method that we followed earlier. With the help of test cases, we have to understand the problem. That makes the easier to write the code, right? So what we have n value and a value and b value, and it is really important to know the definition of the permutations, and I think it's the third time to get this definition of the permutation in this 818 problems, right? So it's nothing but permutation is nothing but it contains only the uh, elements up to equal to n, less than or equal to n, right? Yes, this is and the elements inside them are not having repeated more than one time. So yes, and so as this is the n, it's nothing but the size of the permutation. So so let's take the test cases 1 and 1 1 1. So the size of the permutation is actually 1. Okay, now uh, we have to take two permutations with this one. As there is no need to take the one again, so this is P and this is Q. So if we have doubt, let me take the another Q which having the same elements of P, right? So this is exist. Now the length of the longest common prefix is 1 1 1 same, and common suffix is b from back, so 1 1 same same. So that's why here we have to print s there. But when we are taking 2 1 2, so 2 1 2, what is happening here exactly? So it's nothing but we have size as 2, like shit. Sorry, sorry. So now the n size is actually 2. So 2 means I can take the elements as 1 2 or 2 1, not 3 4 5. The array must does not contains more. So what we have to do, take the size permutation, take the size as 2, permutation size is 2. So let me say this is P and this is Q. Okay, now we have to check the longest prefix of P and Q is actually 1. So by seeing we can say that, so here the prefix is 1 and here it is 2. So it's not possible to get 1 as the longest common prefix. So then it's not possible. So that's why here we have no as an output and 311. So it's also same 311. We have to take the permutation of size 3 in different with the different permutations like 1 2 3 or 3 2 1 or like 2 1 3 or like 3 1 2, many more, but none of them are having exactly the same, both the same common prefix and common suffixes. See here, if it contains a common prefix but it won't contains common suffix, right? So we have to print here also no. And for here 411, so 411 like 1 2 3 4, this is one permutation. I can say that it is P, and let me take a Q permutation as 1 3 2 4. This is another permutation, and here see the length of the common prefixes is actually 1 and length of the common suffixes is also actually 1, so it's there, so it is true. That's why here we are actually printing S. So this is what the problem says. If you understand this one, then we can go further to write how to code it out. Basically, we are thinking like so for this sum, we have to first find the total number of permutations of size. Then, so depending upon the permutations, we have to choose two which having uh, both common prefixes and common suffixes are same, but we don't need to do that much stuff. In CP, the main important role is to observe the patterns and with the help of this, because then only we can write simple code with the help of that patterns, right? So see here, now see this N and A and B. So basically 1 1 1. So the process is completely depending on the A and B. Whenever the permutation actually uh, have the both the length of the common prefixes are same and length of the common suffixes are same equal to B, then we have to print S, right? So the process is completely depending on A and B. So here, see here, we have A and B as 1 1 and 1 2 and 1 1 again and 1 1 again, but n value changes, right? 2 3 4. So when we add A and B and compare it with the 2 n third variable, so let's do that first. So for 1 1, so here the sum is actually A plus B. So A plus B is actually the sum. So A plus B is actually here greater than 1, and for here 2 plus 1 which is 3, okay, it is also greater than 2 n. Here 2 which is less than 3, and here 2 which is less than 4. Okay, we have this after finding the summation of A plus B and related with the third variable which is nothing but n. So for this one we have S, right? And for this two we have no, and for this one we have S. So basically uh, what we have to do, so observe these patterns. Whenever n plus A plus B is greater than 1, we have to print S, right? And if it is true, then we are, for this case also we have to print S, but here the answer is no. So the difference between these two patterns is actually their elements, right? So we can say that whenever A plus B is actually greater than or equal to n if it has two conditions. What are they? If a is equal to like from this, if a is equal to and b is equal to and is equal to n, then we have to print s. Otherwise, we have to print no, right? So otherwise, we have to print no. That's what we follow, right? So what I'm saying here, whenever a plus b is greater than or equal to 1, when and a is equal to b equal to n then print s. Otherwise, if it is not, then print no. So let's see here. So here no, that's why we have no here, and that's why we have no. So why we have yes for whenever a, b, and n are equal? It's because okay, I see. If you take the n value as 2, the size is actually 2, 1, 2, and 2, 1. But when we take n value as 1, the size is only 1. Then this 3 must be equal. So this is for the case which is able to handle only the first case when n is equal to 1 only, not greater than 1 or not even less than 1. Okay, but it is also like use s whenever n value is 0, a value is 0, and b value is 0. But we don't need to think about it, right? So okay, this is up to him. And from here a plus b's value is less than n. Then we can find the difference between them. So n minus a minus b. So here how much difference is them? Here it is 1, and here it is difference is 2. So for one difference we have no, and for two difference we have s. Okay, we can understand that. Okay, whenever the difference is greater than 1, then we have to print s. Otherwise, we have to print no. Okay, so I hope still I don't understand. Let us take the n value as 7. Okay, n value as 7. Okay, so then n value as 7. That means the size of the okay, okay, the size is 7. The elements inside the P is 1, 2, 3, 4, 5, 6, 7 in like in P permutation, and in Q permutation we can say it like 1, 2, 4, 3, 5, 6, 7, and this is what actually present in Q permutation. This is Q permutation, like this is P permutation, and this is actually Q permutation. This is P permutation. Cool. Now, if a value is 2 and b value is 2, so here these two are same and these two are same. These two are also same. Okay. Um, so we can able to get. So we have to print s for this case. But whenever a value is 4 and b value is 4, so 4 plus 4 is 8, and 8 is actually greater than 7. Then what we have to do? We have to check whether a is equal to b is equal to c. It's not possible. Then we have to print no. Can't we get actually yes for this? Let's try to do yes for 4. Whenever we can get 4 as the length of the common prefix of between p and q, 1, 2, 3, and 4. Here we have, let me say, here we have 3, and here we have 4. Then 1, 2, 3, 4, 1, 2, 3, 4. Length of the common prefix is actually same. But length of the common prefix is also Common suffixes are also 4. Okay, which is one achievable. 765, 765, 4 and 4. Okay, okay, it is achievable, right? But it's overlapping. That's why we have to print no for this sum. Okay, it's overlapping. Right? Can't it overlap? Okay, so he must say we have in the fourth test case 1 2 3 4 1 2 3 4 or 1 3 2 4 as valid by. Okay, okay, but the description of test case. Okay, this is just A is B and actually B is A, right? So let's see the code for it. See here, I'm reading N, A, B values. And after that, if A plus B is greater than or equal to N. And I print only S whenever the A is equal to B and B is equal to N. If it is not, I'm printing N. No. Whenever summation of A plus B is not actually greater than N, then we can find the difference. And if difference is greater than 1, then we have to print S. Otherwise, we have to print no. So like you can understand it more clearly the second way, right? So whenever the difference is actually greater than 1, see here 1 2, so 4 minus 2 is actually 2, difference is 2, the difference is 2, and like right. So the difference is 2, is 2, 4 minus 2, the difference is 2, and the permutation like q is like 1 2 3 4, and p like 1 3 2 4. So a and b total summation value, right? This is one, and here a b, if you take this is summation of a and b is actually 2, the difference is actually 2, so which is greater than 1, that's why we are printing s. What if I say here 3, 3 plus 3 here 6. Okay, it's come to the first test case. And whenever 6 is greater than 4, if these 3 are not equal, we have to print no. So it's not possible to get 3, 3 as the same. So that means overlapping is won't allowed it here. Okay, and the difference is actually greater than 1 means, yeah, this is this one prefix and this is prefix, and this is sorry, this is prefix, one is prefix and 4 is suffix. Here this difference, we are actually getting this difference whenever this is actually greater than 1, we are printing s. Sometimes you can get no also, but see here, now let's take the difference which gives 1, that means 3 1 1, this test case. Okay, so like 3 1 1, 3 minus 2, which is the difference is 1, that means 1 2 3, this is the permutation, and like 3 2 1, this is q permutation. Okay, and as the difference is 1, difference is here 1, difference is here 1. Okay, it's not able to achieve because it won't even have the same equal permutation, equal prefixes and suffixes. That's why we have to print now. Okay, so this is about how do you can understand from the test cases. Okay, so I'm sure we can able to solve the first problem of Codeforces contest. because it is always mostly it is under 800 rating, and it's about how can we